Talk about the machine you're probably using at this very moment, your computer. We're going to pull it apart, figuratively of course, and see what really makes it tick. We'll go from its earliest gear-driven ancestors all the way to the insane global network that connects, well, pretty much everything.
Okay, so here's the plan. First, a quick trip back in time. Then we'll look at the computer's body, the hardware. After that, it's all about the brain and the soul. That's the architecture and the software. And we'll wrap up by figuring out how these things actually talk to each other.
So let's kick things off with a look at where it all began. You know, it's so easy to forget how absolutely incredible that little device in your pocket really is. But the road from being a weird mechanical toy to, well, the center of modern life, that journey happened at lightning speed. Let's see how.
Believe it or not, this all starts with gears, not electricity. Back in 1642, you had the Pascaline, which was basically a fancy mechanical calculator. The first idea for a real computer came in the 1830s with Babbage's analytical engine. Fast forward to 1946, and we get ENIAC, the first electronic computer, and this thing was huge. It filled a whole room. But here's where things get really interesting: miniaturization. The integrated circuit in 58 squished a bunch of components together. Then in 71, the microprocessor put a whole computer brain on a single chip. And that, right there, is what made personal computers possible. And finally, in 89, the World Wide Web came along and connected them all. Just to really wrap your head around that jump, think about this. The first computers, they were powered by thousands of super fragile vacuum tubes and took up an entire room. Now, we're in the 5th generation. We've got AI, devices that fit in the palm of your hand, and they're literally billions of times faster. It's not just a step up, it's a completely different universe of technology. Okay, that was the history lesson. So what about a computer today? How's it actually put together? Well, let's start with the stuff you can physically touch, the hardware.
Yep, it's exactly what it sounds like. It's the screen you're staring at, the mouse or trackpad you're using, even the complex web of chips and circuits buried inside the case. But all these physical pieces have very specific and very different jobs. It helps to think about them in categories based on what they do. You've got input devices, like your keyboard. That's how you talk to the computer. Then there are output devices, like your screen. That's how it talks back to you. The processing devices are the brains doing the thinking. Storage devices are the memory. And communication devices, well, they let it talk to its friends. All right, we've covered the body. Now it's time to get inside its head. We're moving past the physical stuff and into the computer's brain, its architecture. This is basically the central nervous system that makes everything work together. And this is the command center. Right at the very heart of it all is the central processing unit, the CPU. A good way to think of it is as an air traffic controller, but for data. Info comes in from your mouse or keyboard, the CPU figures out what to do with it, and then sends it off to the screen, or the speakers, or saves it to your hard drive. Every single thing your computer does goes through here. So yeah, the CPU really is the brain of the whole operation. It's this super powerful little chip that takes all the instructions from the software and just makes them happen. It turns lines of code into what you actually see and do on screen. It does all the heavy lifting. Now, if we zoom in on that brain, we find it has 2 key parts. First, there's the arithmetic logic unit, or ALU. That's the mathematician. It handles all the addition, subtraction, and all the logical if this, then that kind of decisions. Then you have the control unit, or CU. It's the traffic cop telling all the other parts of the computer what to do, when to do it, and where to send the results. So how does a computer actually remember anything? I mean, it's just circuits, right? Well, it all boils down to the tiniest piece of information imaginable. A bit. That's just a single 1 or a 0. An on or an off switch. Put 8 of them together, you get a byte. And from there, the scale just gets mind-boggling. Kilobytes, megabytes, gigabytes, terabytes. Each one is roughly 1,000 times bigger than the last. Now, to work properly, a computer needs 2 different kinds of memory. Think of it this way. Primary memory, which we call RAM, is like your desk. It's where you put everything you're working on right now. It's super fast to access, but it's temporary. When you shut the computer down, the desk gets wiped clean. Secondary memory, like a hard drive or an SSD, that's your filing cabinet. It's a little slower to get things out of, but it's where you store everything for the long haul, permanently. So we've got the body, the hardware. We've got the brain, the architecture. But without instructions, it's just a really expensive paperweight. It needs a soul to tell it what to do. And that soul is the software. It's the ghost in the machine. At the end of the day, all software is just a list of instructions. And it basically comes in two main flavors. You have system software like Windows or Mac OS. Think of that as the building's foundation and the electrical wiring. It runs the computer itself. Then you have application software. These are the tools you actually use, like your web browser or a photo editor. They run on the computer to get a specific job done.
And the absolute king of all system software is the operating system, or the OS. It's the big boss, the conductor of the orchestra. Its whole job is to manage everything, all the hardware, all the other software, and make sure they all work together without crashing into each other. So how do we talk to the OS? Through an interface. The one we all know and love is the GUI, the graphical user interface. That's your world of icons, windows, and clicking. It's visual, it's intuitive. But there's another way, the CUI, or Character User Interface. This is the classic text-based command line. It might look intimidating, but for experts, it can be way more powerful and faster than clicking around. Okay, a single computer is an amazing tool, but its real power, its true magic, happens when it starts talking to other computers. So for our last section, let's connect all the dots and see how these individual machines create the massive network we all live in. When you talk about networks, it's really all about size. You start small, with a LAN, or local area network. That's what connects the computers in your house or in one office. Go bigger, and you might have a MAN, covering a whole city. Bigger still is a WAN, a wide area network, which can span a country or even the globe. In fact, the internet is just the biggest WAN there is. Now, a VPN is a little different. It's not about size. It's like building a secret encrypted tunnel for your data right through the public internet. And how all those devices are physically or logically laid out, that's called the network's topology. It's literally the map of the network. Are they all connected in one long line, like stops on a bus route? Or do they all connect to a central point, like spokes on a wheel? This layout is super important because it determines how data gets from point A to point B. And there we have it, the whole anatomy. We went from the physical body, the hardware, to the brainy architecture, to the software that gives it a soul, and finally to the networks that let them all talk. You can see how each layer is built on top of the one before it. It's an incredible story, from a clunky mechanical calculator to a literal global network in your pocket. It really makes you wonder, if we've come this far in just the last 80 years, what in the world are the next 80 going to look like?